All right, so what is in seawater? There's a lot of different stuff in seawater, depending on the seawater you grab. So, what is some of the stuff we find in seawater? Find dissolved gases. So, just like there are gases in the atmosphere, there are also gases in the water. The gases will dissolve into the water. So, things like oxygen, carbon, and nitrogen gas are also found in water. Sediments, so things like sand or little clay particles or little pieces of like eroded rock or shells can be in the water. Living organisms. So, as we will see in a couple weeks, I believe, there's often a little plankton in the water, or even like things like bacteria will be in the water. So, if you just like get a single cupful, there will still be living stuff in that water. Also, dead stuff. So, you might have little bits of dead organisms, or like little pieces of a dead plant or dead phytoplankton. So, there'll also be dead stuff in the water. Metals. So, you might have stuff like iron, magnesium in there and other salts as well. So next we're going to talk about those salts. The amount of dissolved salt in the water, we call that salinity. So salinity is just basically how salty is the water. So if you took fresh water, like from your tap, that would be very, very low salinity. It actually wouldn't quite be zero because we do have some stuff in our tap water like fluoride and stuff that picks up from the pipe. So it's not like perfectly pure water, which is fine, by the way. But yeah, so that tap water, very, very low salinity. If you added like a couple of tablespoons of salt to it and mixed it up and dissolved that salt, now it's gonna be slightly higher salinity. And if you kept doing that, adding more and more and more salt, it would get higher salinity and higher salinity. Now, when we refer to salts, salts are basically just charged particles called ions. There are two main ones we'll talk about, but there are many different kinds, and any little charged particle can be a salt. We typically measure this in parts per thousand, which basically means the number of grams of salt per 1,000 grams of salt water. So, for example, the average salinity of the ocean is 35 parts per thousand. So, what that means is if you took 1,000 grams of seawater, there would be 35 grams of salt in that 1,000 grams of seawater, of ocean water. So it's kind of showing that. So here's 1 kilogram of seawater, for about a little under, in this case, 35 grams would be salt. And if we broke down those salts into like what elements and molecules are making up these salts, you can see that most of it is chloride, Cl minus. The next big chunk is sodium. We also have sulfate, magnesium, bicarbonate, calcium, and potassium are also all part of the salts that make up seawater. So this is kind of just showing the most abundant salts. I just want you to know the first two, so chloride and sodium. Those are your two main salts in the ocean, and that's also like what primarily makes up like table salt is sodium chloride, sodium and chloride. But there's also sulfate, magnesium, calcium, potassium in the water as well. So it's not just sodium and chloride, but it's mostly sodium and chloride. Now, when we're talking about most of the ocean, especially the deep ocean, which again is like most of it, we talked about how, the ocean covers 70% of the Earth's surface, but it's actually like 99% of the three-dimensional livable space on Earth. So most of that whole volume, the salt levels are very stable. So most of the deep ocean, it is like 35 parts per thousand, like everywhere. So the vast majority of the ocean, it's very, very, very stable. Um, However, at the surface, and especially the surface close to land, you can have some variation in salinity. So, for example, if it rains, you're adding fresh water. So it's like taking a cup of salty water and adding more water to it. So you make the salinity go down. It becomes less salty. Whereas if you have evaporation, that's the opposite process. You're taking salt water, but you're removing fresh water. So it makes it more salty. Or, for example, if you're near a river, right? If the river is dumping a bunch of fresh water into the ocean, the salinity will be lower near the river. So even though most of the ocean has very, very consistent, like 35 parts per thousand salinity, the surface, and especially the surface near land, it can be a little bit more variable. So one of the ways we can look at properties in the ocean are what are called depth profiles. My window right there. So a depth profile shows how something changes with depth. So this is your basic line graph, except it's kind of going in the opposite direction than what you normally see. Normally you see a line graph, it looks like this. It's like if something's going up, it would be like that. This is doing kind of the opposite, where again, it's showing how some property, which is on the x-axis, changes with depth on the y-axis. So this the very top here is the surface of the ocean. And so like this is 1,000 meters down, 2,000 meters down, 3,000 meters down, 4,000 meters down. So again, it's showing how something changes with depth. And you can see on the x-axis here, we have temperature. And so if you look here, 0 is on the left side, so that's 0, and then we're up to about around a little under 25 on the right side. So you can see close to the surface, the temperature is around like 23-ish. And then as you go down, it decreases rapidly. And so once you're down around 2,000 meters, the temperature is only about 2 degrees Celsius. So you can see how temperature changes with depth. So that's a depth profile. So here you can see salinity and how salinity changes. Again, in the deep ocean, it's very stable. So both these lines are like converging right around 35 parts per thousand, right? So again, whole deep ocean is right at like 35 parts per thousand. And these two different lines represent two different locations, measuring salinity in two different locations. So you can see in an area with high evaporation, the it was a little saltier at the surface before decreasing to get to 35. In an area with low evaporation, or maybe even a lot of precipitation, a lot of fresh water being put in, the salinity was a little bit lower and then increased to 35 parts per thousand as depth increased. But again, in the deep ocean, it's pretty much right around 35 parts per thousand. So that's kind of how you interpret these depth profiles. Let's move this back so I can move a little square. All right, put it out of the way. There we go. So for another example, I kind of already went over this, but temperature. Temperature is usually higher at the surface. That makes sense, right? Because you've got sunlight, you've got warm air that's like warming up that surface layer of the ocean. And then in the deep ocean, it's usually pretty darn cold. If you go really deep, it gets down to like close to freezing cold in the deep ocean. So between the warm surface and the deep cold, you usually have a pretty fast change in temperature. So it's not just like one gradual decrease. It's usually hot and then quickly becomes cold. We call that the thermocline. My cat is being annoying. Hi, baby. You want to say hi to everybody? Say hi. Say hello. Say hello. Okay. We call that the thermocline, an area where the temperature changes rapidly with depth. So it goes from being pretty warm to pretty cold fast as you go down. All right, so that is the thermocline. And in general, like I said, the temperature is usually warmer at the surface and colder at depth. Hi, hi. Um, but this is not exactly the same everywhere. So here is the graph I was showing you. This is typically the case at low latitudes, that is latitudes, hi, that are near the equator, so close to the middle of the planet, think like the tropics. But high latitudes, it looks a bit more like this one right here, where it's kind of a line straight down. So I'm asking you, why is it? Why is it at high latitudes, which are areas near the poles, like near the North Pole or near the South Pole, very, very far away from the equator? Why is it that at high latitudes, we see, instead of seeing this like thermocline, we just kind of see this line going straight down? So see if you can figure out why we see this pattern at high latitudes.